conference call is now being recorded.
Okay, good morning. Yesterday we have just started the portion electrochemical machining. So electrochemical machining, this is one of the non-traditional process or machining operation where the electrolysis or Faraday's law of electrolysis is used, or based on the principle of Faraday's law of electrolysis, the machining is being conducted. And we have seen what is a Faraday's law of electrolysis, or what is happening in a electrolysis process. Now, in Easiem or electrochemical machining, here we are using a DC supply. Here you can see a DC voltage of about 10 to 25 volt. 10 to 25 volt is being applied across the circuit. Here the workpiece is kept as an anode. And tool is kept as a cathode. And the required shape to be created on the workpiece is defined on the tool. So based on the shape of the tool, the workpiece is also machined, like you can see in the second figure. Here you can see the shape of the workpiece. This is exact copy of the tool. So whenever the tool is being brought to the workpiece, there will be a gap, and here the circuit will get completed. And due to the electrolysis, the anodic dissolution occurs on the workpiece, where the workpiece is kept as the anode. So anodic dissolution occurs, and the material is being removed. So now you can see the figure. This is another figure. Here also this is the workpiece which is made as an anode. This is a die sinking process, and the tool is kept as a cathode. So this particular shape is being given to the workpiece. Now this is the thing which is happening. Yesterday we have discussed. We have given the DC voltage here. So the circuit gets completed, and the electrolyte, inside the electrolyte, what happens is the water, H2O, water dissociates into H plus and OH minus. This is happening in the electrolyte. And also this is the salt solution. So it contains salt and water. So water dissociates into H plus and OH minus, and the salt NaCl dissociates into Na plus and Cl minus. Okay, and the negative charged particles, that is OH minus and also Cl minus, these things are the anions, right? And these anions move to the anode, that you can see. This moves to the anodes, and this reacts with the ion that is in the anode. That is, here you can see the workpiece. The workpiece what happens is this is the anode or the workpiece. Here what happens is this is the iron metal. After removing the electron or passing through the circuit, what happens is iron dissociates into Fe2 plus 2 electron. Sorry, 2 electron. So this becomes Fe2 plus and this becomes dissociated. And you can see here Fe2 plus. These combines with the Cl minus and OH minus from the electrolyte. So these two combine and forms FeCl2. These two also you can see. And this gets deposited over here. Similarly, Fe2 plus OH minus. OH minus. This also forms FeOH twice. This also gets deposited here. So as a result, the workpiece gets eroded or the particles gets eroded. This is the mechanism. So this is how a typical electrochemical machining occurs. Now we can see which are the basic process parameters in every cases, like the case of USM, EDM, etc. We have many process parameters like voltage, standoff distance, or tool material, feed rate, etc., etc. Here also we have certain process parameters, and we'll see how it can affect the various properties like accuracy, surface finish, MRR, etc. So first of all, we will see which are the process parameters, different process parameters and their values. Okay, so the process parameters. Okay, various process parameters. What are the various process parameters? First one, supply voltage. Regarding the supply voltage, supply voltage used is we have already seen 10 to 20 volt. Then the current is about 50 to 5000 ampere. Then the gap between the electrodes, electrode gap, electrode gap is typically about 0.1 to 0.2, 0.1 to 0.2 mm. Then regarding the tool material, which material? Tool material, typically the tool material, that is a material used as a tool, not the workpiece. Tool is copper, brass, and steel. Fifth one is the tool feed rate, the rate at which the tool is being fed to the workpiece. That is a tool feed rate. Then electrolyte composition and temperature. The composition of the electrolyte. Here in the example, we have seen the brine solution or the salt solution. Whether the concentration is much higher or lesser, or what are the constituents of the electrolyte. That is the electrolyte composition. And also the temperature which is maintained. temperature. Then here the MRR, usually the MRR value is about 1600 mm cube per minute. This is the usual MRR at 1000 ampere. Okay, and surface finish. Regarding the surface finish, it is about 0.1 to 0.5 micron. And one more thing, specific power consumption. The power consumption, specific power consumption. Value 7 watts per mm cube per minute. So these are the basic process parameters: supply voltage, current density, current, electrode gap, tool material, tool feed rate, electrolyte composition and temperature, MRR value, that is 1600, and it is dependent on the current density, surface finish 0.1 to 0.5 micrometer, specific power consumption. Okay, so these are the main process parameters included in the electrochemical machining. Now we have already seen the electrochemical machining in the real time. You can see here in the real time it is like this. Here you can see the workpiece. This is the workpiece. This is kept as a cathode, that is connected to positive terminal, and this is the tool. Here you can see inside the tool the electrolyte is being fed. This is the actual figure. So from this hole you can see the electrolyte is passing through the tool and to the portion of the workpiece, or the gap or machining portion it will be provided. And here you can see an insulation. Why it is being kept? In order to prevent the radial machining. Otherwise here also the machining will be done. Okay, so in order to have a good accuracy cut, we are providing the insulation. And you can see the basic procedure here. The electrolysis, using electrolysis, electrochemical machining is being done. This is just a figure, and from here you can see 3 stages: first, second, and third stage. Here it is given as 3 stages. Primarily, it starts machining this portion. This is the, for example, this is the required dimension or required shape to be made into the workpiece. So while it is brought to the workpiece, it starts machining. You can see here in the second figure, as the distance decreases or it approaches more and more material is being removed like this, and finally the end shape is being produced. Okay, so now you can see what are the main advantages of Easiem process. Like many other EDM and all, we have seen certain advantages, limitations, applications. Here also we have certain advantages. We'll see. Advantages of Easiem or electrochemical machining. Okay, so first one, Machining of hard and brittle materials with good surface finish. So it is possible to machine hard and brittle materials with good surface finish. So with good surface finish itself, you can able to machine good hard and brittle materials. Then comes for the complicated shapes. Complicated shapes. As we have seen in the last figure, any complicated shape can be made into the workpiece by just defining the tool shape just opposite to that of the required shape. So the complicated shapes can be created. Okay. Then here there is no direct contact of the tool and the workpiece. So usually there is a no or negligible tool wear. Negligible tool wear. And also due to the same reason, that is there is no direct contact of the tool and the workpiece. So there is a absence of a force or direct force on the workpiece. Here the tool is not forcing the workpiece. So there is no mechanical or thermal residual stress. So no mechanical or thermal residual stresses on the workpiece, on the work. Then regarding the surface finish, there is a good surface finish. And one more, MRR. Regarding the MRR, this is not dependent on the material hardness, whether it is hard or ductile. In some cases, that is in USM, material removal is possible only for the hard materials, and it is not suitable for the ductile materials. And there we have seen, when the hardness decreases, MRR decreases. When the hardness increases, MRR increases. But in electrochemical machining, whether the hardness is much or smaller, it is not depending on that value. That is, MRR is independent on material hardness. So these are the main advantages of Easiem. First one is, it is very suitable for machining hard and brittle materials with good surface finish. Next is the here you can prepare or make the complicated shapes. Then we have seen there is no direct contact. There is no direct contact of the tool with the workpiece. So that's why there is no tool wear or even negligible tool wear. And for the same reason, we can say there is no mechanical or thermal residual stresses on the workpiece, because there is no direct forcing or no direct contact of the tool with the workpiece. Then we have seen regarding the surface finish, we through this process, electrochemical machining, a good surface finish is possible. And finally, we have seen that is a dependency of the MRR with the material hardness. That is, it is independent of, and or it is not dependent on the material hardness. That is, whether it is hard or or the hardness value is less or more, it is not depending on that for the MRR or material removal rate. So these were the main advantages. So like the advantages, there are main certain limitations also or disadvantages. So we will move on to that. So what are the limitations or disadvantages of Easiem, electrochemical machining? The first thing is like in EDM, this is suitable only for the conducting materials because the process is based on the principle of electrolysis, and the workpiece is made as the anode, so it should be conducting. So non-conducting materials cannot be machined. That is electrically non-conducting materials cannot be machined. This is the main disadvantage or the limitation of an ECM process. Now, here you are dealing with the electrolyte, which is having different compositions, and there may be a chance to corrode, or depending on the nature of the electrolyte, there may be a chance to get. Sometimes it may react with the tool or the workpiece, and it may affect the process. That is, if it is reacting with the tool, means there will be tool wear, and if it is reacting with the workpiece, then the actual dimension won't be able, or there will be the alteration in the finish. So regarding the stability, that is, the tool and workpiece should be chemically stable with the electrolyte. So tool and workpiece should be stable with the electrolyte. Otherwise, what happens is it may react with, or it may chemically react with the tool and forms a tool wear, or it reacts with the workpiece, and it may cause the deterioration in its accuracy or its surface finish. Then the feed rate, regarding the feed rate, it should be controlled. So accurate feed rate should be maintained. Otherwise, the required shape will not be done, or the dimension or the control is very difficult. That is accurate feed rate. Accurate feed rate. Accurate feed rate is required of tool. Is required. So the feed rate should be accurate. Next is the regarding the cost and the dimension control. High cost. So here the cost is high, and also dimensional control. Regarding the dimensional control, it is difficult in controlling the dimensions or the dimension control. Difficult in the dimensional control. Then this is usually done by the electrolysis, and there is no direct contact of the tool. So usually the material removal takes place by the electrolysis process or anodic dissolution. So there will be a difficulty to create sharp corners, like the sharp corners. It is not possible, or there will be always a rounded surface. So that is the main other limitation. So inability to machine sharp corners. Machine sharp corners. And finally, regarding the power consumption, it is much higher. So large power consumption. So these are the main limitations of electrochemical machining. So first of all, it is being used only for the conducting materials like Easiem process. So electrically non-conducting materials cannot be machined. Then regarding the electrolyte, whether if it is reacting with the tool material or the work material, then there may be a chance to have the tool wear, or it may react with the workpiece to create the decrease in the accuracy or surface finish. So the tool and workpiece should be stable, chemically stable to the electrolyte. And third is the accurate, that is the need for accurate feed rate of the tool. The feed rate should be maintained accurate. Then regarding the cost, the high cost of the equipment. And finally, the regarding the dimensional control, that will be little bit difficult in controlling the dimensions. And also regarding the machining of sharp corners or interiors, etc., there will be an inability, or it is not easy to machine sharp corners or sharp interiors like you have seen there. And finally, regarding the power consumption, there is a large or huge power consumption while using the electrochemical machining. So these are the key disadvantages, and you can see the applications where this process, electrochemical machining, can be used. Electrochemical machining. First of all, in aerospace industries. Aerospace industries. In aerospace industries, this Easiem process mainly used in machining the various parts like dies, turbines, compressor blades, etc. That is dies, turbine, compressor blade, etc. In those things, we mainly use electrochemical machining. Then machining other general parts like machining general parts. General machine parts like chain pinion, driving joint, pump gland, impeller, etc., etc., connecting rod, hydraulic spool, gear wheel. So chain pinion, chain pinion, chain pinion, driving joint, driving joint, driving joint, pump gland, impellers, etc. Then, in order to have the complex 3D surfaces, there we use this Easiem process, that is phasing and turning operations, phasing and turning of complex 3D surfaces. So for complex 3D surfaces, this phasing and turning operation can be done using electrochemical machining. Then we have already seen a figure for die sinking. In die sinking, we use the electrochemical machining. And also for deburring. So usually in the machining operations, there will be some burr in the final product. So in order to deburr or deburring of parts, for example, gears, as seen in gears, this can be used, that is electrochemical machining can be used. So these are the some of the important applications of electrochemical machining. So first of all, aerospace industries. In aerospace industries, we have seen in dies, turbines, compressor blades, etc. And regarding machining, other machining parts like chain pinion, driving joint, pump gland, impeller, connecting rod, etc., etc. Then phasing and turning of complex 3D surfaces. Then regarding the die sinking, and finally deburring of the parts like gear. So these are the main applications. Now, so this is your today's class. Tomorrow you will see what are the main properties of electrolyte and material removal mechanism, how the mechanism regarding in case of the calculations in terms of calculations, and finally the influence of various process parameters. So that will be the end of your third module. Okay.